Ever notice how, like, different liquids flow differently?
Oh, absolutely.
Like, if you pour honey versus water,
Yeah.
the honey's thick and slow, and water just kind of goes everywhere.
Right, right.
Why is that?
So that difference all boils down to something called viscosity. It's basically how much a fluid resists flowing, like internal friction. Honey's got high viscosity, so it's all, nope, not moving fast. Water, low viscosity, so it flows really easily.
Okay, so viscosity is about how easy it flows,
Yeah.
but how's that tied to the actual movement?
To get that, we got to talk momentum.
Okay.
Basically, it's the mass of something in motion, like how much oomph it's got. You get it by multiplying mass by velocity. And with fluids, understanding how momentum transfers is super important.
Makes sense. So a fluid's momentum is tied to its speed.
Yeah.
But fluids aren't solid blocks, right?
Right.
They've got layers that move at different speeds.
Exactly. And because of that, we get something called shear stress. Imagine those layers trying to slide past each other. That stickiness, the resistance between them, that's shear stress. The higher the viscosity, the stronger the stickiness, and the harder it is for everything to flow smoothly.
Ah, so it's like the layers are pulling on each other.
Yeah.
And if it's sticky, they got to pull harder.
Perfect way to put it. And this shear stress isn't random. It's directly related to something called the velocity gradient.
Velocity gradient.
It's just how much the fluid speed changes over a certain distance. Think of a river. It's fastest in the middle, slows down at the banks.
Right, right.
That change in speed, that's the velocity gradient.
So the steeper that gradient, the harder the layers are pulling, more shear stress.
Precisely. It's all linked. We can actually describe this with a nifty equation. Oh, you duty.
Oh boy, math. Explain that like I'm not a physicist.
Basically, it says the amount of shear stress, that's equals the fluid's viscosity, times how steep that velocity gradient is.
Yeah.
So high viscosity and a big speed change over a small distance means a whole lot of shear stress going on.
Uh-huh. So that's why honey's such a pain to pour. Even a little speed difference makes a ton of shear stress because it's so viscous.
Exactly. But the real puzzle is, how does shear stress move that momentum around within the fluid?
Okay, yeah, good question.
And to answer that, we got to dive into a key equation in fluid dynamics. You ready for this?
Get me with it.
The Navier-Stokes equation.
Ooh, sounds intimidating. What's so special about it?
It's basically the equation that describes how fluids move, like at a fundamental level. And there's this one term in it that captures how momentum spreads out because of viscosity, going from areas of high momentum to low momentum. We call the diffusion of momentum.
So it's like if you drop dye in water,
Yeah,
how it spreads out. It's like that, but for momentum instead of color.
you got it. Similar concept, but it's momentum diffusing, and that's all thanks to viscosity.
Okay, so viscosity isn't just how easily something flows. It's key to how momentum gets around inside. But like, why should I care about momentum diffusion? Is this just theoretical, or does it matter in real life?
Oh, it matters big time. Engineers use this to design everything from pipelines to airplane wings, like predicting how fluids behave, making things work better.
Wow, so pouring honey leads to equations that explain how, like, the whole world of fluids works. Crazy how much is going on we don't even see.
Right. And it gets even cooler when we talk about different ways fluids can flow. We got to consider laminar flow versus turbulent flow.
Okay, I'm listening. What's the difference?
Laminar flow, think of honey oozing out of the jar, everything's smooth, orderly, viscosity's in charge. But turbulent flow, that's when things get wild.
Turbulent.
Yeah.
Is that like if you shook the honey jar instead of pouring it?
Exactly. You get all these swirling eddies, the speed changes unpredictably. It's way less predictable how momentum gets transferred.
So stirring your coffee gently versus shaking it like crazy. Gotcha. But how do we go from smooth to chaotic?
That's where things get even more interesting. It all comes down to the Reynolds number.
Another new term. All right, lay it on me. What's this Reynolds number all about?
Basically, it tells us if a flow is going to be laminar or turbulent. Takes into account viscosity, density, velocity, and like a size thing, like the diameter of a pipe. Low Reynolds number, smooth sailing, laminar flow. High number, buckle up, it's turbulence time.
So this number tells us if it'll be a smooth ride or a wild one.
You got it. And knowing about this switch is super important for understanding how fluids act in real-world situations. Yeah, it's amazing how one number can tell us so much about how a fluid's going to act.
So let's say I'm pouring that honey nice and slow from the jar. Low Reynolds number, laminar flow. Right.
Right?
But if I shake it like crazy, things go turbulent. What's actually going on in that switch?
Okay, so picture that smooth laminar flow in a pipe. As we speed things up, tiny disturbances pop up, like little ripples or wobbles in the flow.
What causes those? Is it like imperfections in the pipe itself?
Could be. Even a tiny scratch can trigger them. But it's not just the pipe. Vibrations from outside, even temperature differences in the fluid can mess with things.
So even if everything seems perfect, there's always a chance for some chaos.
Exactly. Now, in laminar flow, viscosity kind of smooths things out. It dampens those disturbances, keeps it all nice and predictable. But as that Reynolds number goes up, viscosity's grip weakens. Those little disturbances, they start to grow.
Like little seeds of chaos just waiting to explode into full-blown turbulence.
I like that. As they grow, they start bumping into each other, creating all these crazy flow patterns like a chain reaction. And eventually, bam, it's full-on chaos, unpredictable. That's turbulence.
From tiny wobbles to total mayhem. And that's where turbulent viscosity comes in, right?
Exactly, because in turbulent flow, those big swirling motions, they call the shots on how momentum gets moved around. It's not just that smooth diffusion we saw in laminar flow anymore. We got to factor in all the extra mixing and energy transfer happening in this chaotic world of turbulence.
Which is why we need a different kind of viscosity to describe it all.
Exactly. Turbulent viscosity basically tells us how much more resistant turbulent flow is compared to laminar flow. Like, imagine stirring honey with a whisk.
Okay.
The faster you stir, the harder it gets, right?
Yeah.
That's kind of like turbulent viscosity. The crazy mixing makes the flow resist more.
Okay, so we've covered laminar, turbulent, and that Reynolds number, calling the shots on which one we get. Crazy how much is hiding beneath the surface of, like, just a fluid moving.
It really shows how connected all these ideas are, and the deeper we go into fluid dynamics, the more we realize there's so much more to learn.
Speaking of learning more, are there any areas of fluid dynamics, especially related to momentum diffusion, that are, like, really exciting or tough to crack right now?
One of the biggest puzzles is turbulence itself, understanding it in all its craziness. It plays a part in everything, weather patterns, how efficient airplane wings are.
So even though we know it's important, there's still a ton of mystery surrounding it.
Absolutely, and that makes it even more fascinating. We're always coming up with new ways to try and figure out how turbulent flows act. One approach is direct numerical simulation, or DNS for short.
DNS, does that?
Basically, we use super powerful computers to solve that Navier-Stokes equation directly. It lets us see all those tiny eddies and chaotic bits that make turbulence what it is. It's like a virtual wind tunnel inside a computer.
That's so cool. So can't we just use DNS to solve all our turbulence problems?
I wish. The problem is DNS takes a ton of computing power. Even with the best computers, it only really works for fairly simple flows. For more complex stuff, we have to use other methods like large eddy simulation or LES.
Okay, so what's the difference between DNS and LES?
LES tries to find a balance between being accurate and actually being doable on a computer. Instead of trying to see every tiny detail, we focus on modeling the biggest eddies directly, those big swirling motions we talked about. The smaller turbulent fluctuations are then dealt with using simpler models.
So it's about getting the main idea of the turbulent flow without getting lost in all the tiny details.
Right.
But even with all this fancy tech, we still don't fully understand turbulence, do we?
You got it. There's still a lot we don't know. One big mystery is how energy moves between different scales of motion in turbulent flow. Imagine a waterfall, cascading down from the biggest eddies to the smallest swirls. We're still trying to map out all the paths that energy takes as it travels through this turbulent flow.
Sounds like a pretty complex dynamic process. Yeah, it's wild to think that something we see all the time, like water flowing from a faucet or wind blowing through trees, can be so hard to wrap our heads around.
It really shows you how complex nature is. And this whole turbulence thing, it goes way beyond everyday fluids. We're talking astrophysics, climate science.
It's not just pipes and wind tunnels. It's the gases and stars, ocean currents, even the plasma infusion reactors.
Exactly. The same ideas about turbulence we've been talking about, they apply to all sorts of stuff, from tiny things to the biggest things in the universe.
It's crazy how these concepts we've been going over connect to so many different areas of science.
That's one of the things that makes fluid dynamics so cool. It's always changing, pushing what we know, and showing us new connections between things that seem totally different.
So next time I see a cloud swirling or a river rushing, I'll be thinking about all that stuff going on behind the scenes. Viscosity, momentum diffusion, those chaotic eddies, a whole hidden world shaping what we see.
And remember, we're still learning about fluid dynamics. Every new discovery, every new piece of tech just opens up more questions and challenges. It's a field that's wide open for exploration, full of potential for big discoveries.
Well, this deep dive has definitely given me a new appreciation for how intricate and, beautiful fluid motion is. It's both amazing to look at and super important for understanding our world. Thanks for taking us through all of this.
It was my pleasure. And remember, curiosity is what drives science forward. So keep asking questions, keep exploring, and keep being amazed by the fluid world all around us.